Good morning, everyone. This is Rebecca Bailey, and I will be your moderator for today's webinar. Welcome to the May webinar. I hope that everyone around the world is doing well. Just on a housekeeping note, today's speaker will be taking questions at the end of the webinar. So if you can enter your questions at any time during the webinar into the questions box that is on your GoToWebinar side panel. He'll be happy to take the questions at the end of the webinar. So for today's webinar, I'd like to welcome Dr. Paolo Denti. Paolo is an associate professor of pharmacometrics in the Division of Clinical Pharmacology at the University of Cape Town in South Africa. He holds a Master of Science degree in computer engineering and a PhD in biomedical engineering from the University of Padua in Italy. And I hope I pronounced that right. And I'm sorry if I did not. He joined the University of Cape Town in 2009, where he and his team of pharmacometricians apply mathematical modeling to better characterize the PK and PD of the treatment of HIV, tuberculosis, and malaria, and thus inform how to optimize dosing regimens. A focus of their research is on neglected populations, such as pregnant women, young children, and TB HIV co-infected patients, for whom the current dosing guidelines lack empirical evidence and are often based on inadequate extrapolations. This puts these vulnerable patients at risk of poor treatment outcomes. So with that, I would like to thank Paolo for coming and giving the webinar, and welcome, Paolo.
Thanks, Rebecca. I hope you guys can hear me loud and clear. Thanks for the introduction, and thanks for giving me the chance of presenting this to the audience of the webinar, which I understand is mostly constituted of experienced pharmacometricians. So as you can see, the title of my talk is of clever models and dumb spreadsheets, what is more effective to drive policy. And even though this may not be as welcome to an audience of pharmacometricians, and it wasn't to myself either, sometimes spreadsheets can do the job. So I hope I'm gonna take you through the whole presentation, and then at the end you can tell me if you agree or disagree. And in fact, I would understand if you disagree as well. So as Rebecca already said, this is something about me. I'm from Italy, as you can probably tell from the accent. I studied at the University of Padua, and this is somehow going to come back in the presentation as well. Then I did my PhD partly in the States, and then I moved to beautiful Cape Town around 10 years ago. So we did a bit of chit-chatting with Rebecca and Patrick just before. And as I understand, I have to say good evening, good morning, good afternoon. Rebecca told me that some of you guys actually have the luck of listening to this in an auditorium for a lunch break. Most of the other people are probably in a similar situation to the one in the picture here, sitting in their pajamas in their bedrooms. Here in Cape Town, it's 6 p.m., so it's 1 hour late for gin and tonic, but I'm going to delay 1 hour today. And just to make this a bit less awkward, this is me, picture taken on the balcony this afternoon. I swear I am wearing trousers, but that's just to make it a bit less awkward. Lockdown version. Here in South Africa, we've been in lockdown for 2 months now. As you can see, there's no barber shops open, and while the shaving is I've just been a bit lazy, that I have to confess. Okay, so let me start with the outline of the talk, because in spite of the very sort of joking title, the topic itself is actually quite serious, and it's about dosing in children, and in particular dosing in children for neglected diseases, or those that don't make money, let's say. So I'm going to discuss what the principles of dosing in children are, the science that is behind it, and just, this is a problem that has been studied a long time, and I don't want to claim credit for it, but I'm going to give an overview of what is known about what principles one should use for dosing in children. And then I'm going to pause and take a look at whether all this science that has been produced for centuries, in fact, has gotten to affecting the policy and helping us decide how to dose children. I'm then going to talk about the WHO pediatric dosing tool, which is where my contribution came to be. I discuss what we've done with it, what are the advantages and disadvantages of it, the obvious limitations, which most modelers in here are going to see quite clearly, and then I'm going to talk about a project in which we are implementing this tool with a Shiny app to make it a bit more flexible. So yeah, to introduce the topic, as I mentioned, what we are looking at is how to dose in children. My work at the University of Cape Town is mostly focused on tuberculosis, HIV, and malaria. And for some of these populations, the majority of drugs that are used, the license has expired, at least in developing countries. So there is very limited drive for companies to produce child-friendly formulations. So I cooperate, myself and collaborators are part of a WHO task force, whose aim is to gather consensus on what the right dose for the different drugs is in children, and also to help the creation of child-friendly formulations. Because since there is relatively little money to be made from these formulations, WHO tries to reach consensus amongst experts on what formulation should be prioritized, and even more specifically, what strength of the formulation should be, and if it's a fixed drug combination, what different components and in what dose should be included in the tablet. So this is the framework within which my work fits in. So dosing in children is actually quite a difficult thing in general, meaning there are lots of factors that must be kept into account. And working in anti-infectives as an advantage because we are somehow in a privileged situation. So the FDA released a decision tree, which is displayed here. We're going to walk through it just now, that summarizes the steps that one needs to follow if you want to design studies to register a drug in children. And there are some easy questions to follow, and you can end up in a different branch of the tree. So if we try to climb this tree for anti-infectives, we are quite lucky, because the first question is it reasonable to assume that children, when compared to adults, have a similar disease progression and response to intervention? And while there are some differences, because the disease is not exactly the same, at the end of the day, when the pathogen is the same, the illness tends to be similar. This is, for example, the case in HIV. So we choose yes to both, and we'll end up in this other cell, which asks, is it reasonable to assume that there is a similar exposure response in children when compared to adults? And once again, the answer here is yes, because the pathogen is the same. So one can assume that if we do manage to achieve the same concentration in children as in adults that get successfully treated, well, then the drug should work just as well in children. So in this case, the FDA recommends that PK studies are conducted in children, aiming at finding the dose that can achieve similar drug levels to those in adults, and then of course monitor safety. So for anti-infectives, after climbing the whole tree, at the end of the day, all we have to do is target the same exposure as used in adults, monitor safety. So we have to basically just characterize the PK in children. So the questions we need to answer really is, what is the adult equivalent dose that we want to give to a child? And the next question that underpins this one is, how do the physiological processes scale from adult to children? How does pharmacokinetics change between adults and children? So one first guess that one could use is to just assume that everything just scales linearly, and this is done very frequently. So if we just assume that PK scales linearly with weight, well, then why don't we just give the same milligram per kilogram dose to children as we do in adults? Well, turns out this doesn't work, and the reason why it doesn't work is the same reason why these monsters over here, I hope they are appearing on your screen, are unlikely to exist. So every time I present allometric scaling to my students and I show these slides, I tell them, can you guys tell me why these monsters, these huge spiders, could not exist in real life? And they always tell me, well, what would they eat? There are no flies big enough. And sure, that's a valid point, but there are actually more how can I say, more basic reasons why they actually would be inconsistent. They couldn't exist. And this is a problem that has been studied for a while. And here is where the University of Padua comes back, because one of the first people that studied this is actually Galileo Galilei, who was a professor in my alma mater some 4 centuries before me. And some of you guys may just know him because he features in the chorus of one of the best songs ever, Bohemian Rhapsody by Queen. But he was also a scientist, and he was the one that is famous for dropping spheres of different weight from the Leaning Tower of Pisa and measuring time. So one of the fathers of modern science. And amongst the different topics that he studied, in fact, he also studied allometry, which is the effect of body size of the morphology of living beings. Now I found this comic on the web. I hope it's fake news. Hopefully Galileo didn't drop different animals from the Leaning Tower of Pisa to do his studies. But funny enough, he really liked things falling off, because what he says is it not obvious that if a horse falls from a certain height, they're going to break their bones, while if a dog or a cat falls from a much higher height, they will suffer no injury at all. So if things really were to scale linearly, how do you explain that an animal much bigger than a cat cannot withstand a proportionately higher fall? Similarly, he went further. Hopefully the ethics committee in the 16th century didn't allow this either, but even children, if they fall from a certain height, they'll be fine. Whereas if an older person fell from a proportionately higher fall, they would kill themselves, they would die. And this has been known for a while. In fact, this was published in 1638. And it basically boils down to the fact that nearly 400 years ago, it was already clear that scaling things linearly doesn't necessarily work. So not all biological processes scale linearly with weight or with size. So if we go back to our giant spider, we take a tarantula and we blow it up 100 times, so we make it 100 times longer, or even 1,000, what is going to happen? What happens is that if we make that spider 100 times longer, then the volume of the spider would be 1,000,000 times bigger, because the volume grows with the third power of the length. So this spider will be 1,000,000 times bigger in terms of weight, but then the section of its legs, which is a surface, would only increase 10,000 times, because it scales with a square, not with a cube. So what happens here then? That basically, if you just took the spider and you just made it bigger without changing any proportions, the legs of the spider would need to carry 100 times more weight per square meter. And that's not possible, because the same material cannot withstand that additional pressure, so the spider would collapse under its own weight. So scaling things linearly is dangerous. It doesn't quite work all the time. So now we don't care about giant spiders, we were talking about pharmacokinetics, but the same principles apply to pharmacokinetics. So different parameters may scale differently. And here I have the overview of the basics, basically. If one looks at volume of distribution indeed scales quite well with body weight. So as long as the body composition remains similar, one can assume that volume of distribution scales linearly with weight. With clearance, things are a bit more complicated, because clearance tends to have to do, it relates to surfaces of contact between the tissue and the blood vessels. So since the weight, increases with the volume, and the surface only with the second power, this would lead to a discrepancy between the exponents. So the exponent that one should use to scale for weight in clearance would be 2/3. As it turns out, it's actually not 2/3, because this has been studied further. And yes, you see correctly in there, this is a study from 1932, where basically Kleiber looked at metabolic rate. So the chart that you see over there is log metabolic rate, so how much heat each living being emits over log weight in kilograms. And you see that this is valid across species, but in there you also have a man and a woman, and you can imagine that a child is somewhere over there. So this slope is actually 3/4. This may sound like magic, but it's due to the fact that the surfaces in our body are not entirely conventional surfaces, but they are more similar to, they're more easily dealt with as with fractal geometry. So very loosely speaking, they are very, very convoluted curves, so that the dimensionality is slightly different. Why did I put a picture of that thing over there on the left? Well, that's I don't know if you've seen it before. It's a Romanesco broccoli. It's one of the most beautiful vegetables, and I think it summarizes well sort of the fractal structure of it. It's not as delicious as it looks, but I thought it conveyed the idea very well. So at the end of the story, volume scales linearly with weight, clearance scales with an exponent of 3/4. So if we have to put everything on a chart here, I have summarized the two concepts. You can see that you have on the y-axis a certain fraction of reference, and I have chosen a 70-kilogram patient as the reference weight. And on the x-axis, you have the different weights. You can see that if you scale volume with an exponent of 1, that's just a straight line. If you scale clearance with this 3/4 exponent, the curve is slightly different. They look like they're very similar, but there are some important differences in the ratio between them, especially for the lower weights. And once again, I think that for those of you that work in pediatric drug development, and in general for most modelers, this was fairly obvious. This has been widely published. It's everywhere. In fact, for those of you guys that have attended PAGE last year, you might have seen that this is so popular that in fact Nick Holford even put it on his pharmacometrics Tinder profile. And the fun part about a webinar is that I don't know if you guys are laughing or not, and even worse, I don't know whether Nick is in the audience and if he is laughing or not. But that's just to say that none of this is entirely new, and I don't claim any credit on it. This is all known. So is it this simple? Is it really that easy to do? Well, actually, if you want to scale between adults and children older than 2 years of age, yes, it is actually that simple. This works really well, and the predictions are actually very accurate. For younger children, things get a bit more complicated, because younger children, younger than 2 years of age, and the more we go towards neonates, for them, besides the effect of body size, also age matters, because the organs of these young children are not only smaller, but they're also not mature. So the enzymes may not work as well, the kidneys may not be as efficient. So there is an additional factor which needs to be included, which is maturation. And this has also been characterized for different metabolic pathways, but it is drug specific. So different drugs use different routes of elimination, which of course are going to mature differently. So this part is a bit trickier. So for younger children, there is a bit more thinking to do, and the predictions in general are not entirely accurate. But let's see what is going to happen to exposures to a drug if we include all this science in the picture. So we start from a chart where on Y we have the exposure expressed as percentage of a reference. Once again, we're going to choose a 70-kilogram person as reference, and on X we have the weight. So if we choose a 70-kilogram person as a reference, then because of the effect of allometric scaling, if we dose children the same milligram per kilograms, they are going to achieve a lower exposure. And you can see the curve that goes down, and for a very small, for a child of around 10 kilograms, you can see that they are expected to have already a 35-40% lower exposure. For younger kids, though, maturation kicks in, and that has the reverse effect, meaning that given their size, these children are immature and their clearance pathways don't work as well, so they start clearing the drug less well, and they need a lower dose. In reality, things are even more complicated in this lowest range, because on top of the simple maturation, there are a whole bunch of other factors, some even very practical, that may affect what goes on over there. And indeed, part of this is actually due to the fact that we don't have proper formulations for children. So what could happen is that in small children, tablets need to be broken or crushed. They need to be swallowed. And we do know that the bioavailability of pretty much anything in small children, even spaghetti, is not exactly 100%. It's very variable and quite unpredictable. So for those very young children, things get tricky, but for the older ones, it's quite easy. So summarizing all of this knowledge that has been there for quite a while, so long, pharmacokinetics in children older than 2 years of age is pretty much fully predictable. So that means that without even giving a drug to a child and drawing a single blood sample, we could pretty well predict what the PK is going to look like, and it's known that they need a larger milligram per kilogram dose with respect to adults. For infants lower than 2 years, younger than 2 years of age, things are more complicated. They become drug specific, and one can be smart, use physiologically based PK modeling or some other a priori assumptions. But in general, those predictions need confirmation in the younger children. However, and this is the question that really matters, all of this knowledge, all of this science, is it getting to policy? Are we actually using all this science to inform how we dose children, at least for the older children, the ones that we know we are able to predict very well? Well, the sobering answer to this can be done very quickly. And here what I've done is I've Googled the WHO guidelines for the dosing of antibiotics in children. And this is quite a hot topic, because we know well that antibiotics, some are toxic, so of course there is that problem. But the other issue is that if you achieve low concentration of antibiotics, you run the risk of having subtherapeutic concentration in children, which may breed resistance, which is one of the challenges of the next century, according to the WHO. So, well, we look at this table, and you've probably seen it already, that actually for each single one of these drugs, the target is the same milligram per kilograms per day, irrespectively of age or weight. So here you see that this applies to all children between 2 months and 12 years. In fact, for some of the other drugs, it goes all the way to 18. So all of the science, all of this knowledge has not gotten there. I focused on one of these drugs, which is levofloxacin, which is used for multi-drug resistant tuberculosis, amongst other things, because that's one that we actually studied in our lab. So with some collaborators, here is a paper that came out on that. We sampled a cohort of MDR-TB children in South Africa that got dosed according to WHO guidelines, and surprise, surprise, we found a curve that looks entirely similar to the one I have shown before. When you use flat dosing, the exposures go down until a certain weight, and then they start going back up again when the maturation kicks in. So this curve was confirmed in the data, but most of it could have been predicted without giving any drug to any children. We then proceeded to use modeling to devise a weight-banded dosing. And you can see that in this case, we were actually targeting an adult exposure of equivalent to 750 milligrams. The average TB patient is around 50 kilograms. So we were targeting an adult dose of 15 milligrams per kilogram. You can see from the range over here that, as predicted, most children need higher milligram per kilograms doses until we get to the very young ones that are immature. So the question now is, why is all this knowledge not being used? So for some drugs, the information is not known, but even for the ones that is known, because we have, people have run studies, well, it looks like it doesn't actually get there. It doesn't get to policy. Why are we not achieving in actually using this knowledge? Well, probably because allometry is nonlinear, so it's non-intuitive. One can argue that the therapeutic range of these drugs is not always that narrow, so one doesn't actually see the difference in single patients, but one has to think that here we are looking at policy. So we have to make a decision once, we have to give people a table on how to dose children, and hundreds of thousands of children are going to be dosed based on that. So we might as well do it properly and make sure that the average child is dosed correctly, and this is going to prevent sort of the outliers from going outside of the range. So we have all these clever models, but they're not getting there. So what can we do? Well, maybe we have to take our clever models and just dumb them down a bit and try and make the results a bit more digestible. So what I have done is basically try to implement the same features that we use in our PopPK models in non-memory monoliths and just sort of simplify it into an Excel spreadsheet. So why have I done this? Because when I joined the pediatric antiretroviral working group at WHO, I saw that they were using a generic dosing tool to basically visualize what milligram per kilogram dose they were giving to children in different weight bands. This comes from the fact that, of course, most drugs are available in tablet, which has a certain size. And of course, you want to avoid breaking the tablets if possible. So what you do is you basically say, okay, all children between 10 and 14 are going to get 3 tablets, and then you break, the weight range into weight bands and give less and less tablets. So what this tool was doing, it was targeting the same milligram per kilogram dose and displaying it so that while advising on the weight bands and the dosing, the experts could check that the milligram per kilograms did not exceed the recommendations. So I knew that this tool was actually quite nice. The only problem was that the target is known to be wrong, because we know that because of allometric scaling and maturation, using the same milligram per kilogram dose is not a good idea. So all I've done is I have redesigned the tool and I actually make it look very similar to the previous one, but underneath the tool is accounting for the effect of allometry, and instead of targeting the same milligram per kilograms dose, it targets the equivalent AUC to the reference. So what the user does, as we'll see later, you just set the size of the adult that you're treating in terms of body weight, the dose that you give, and that is used as a reference in the tool, and the tool automatically adjusts for allometry and tells you, and basically displays as the reference line the dose that the model predicts should be given to achieve the same exposure. The tool also displays, as you see on the right over there, the expected exposure in the smallest and largest child within each weight band, so that if those two diverge too much from the reference, maybe it's time to break the weight bands further. So what the user does is they play with a number of tablets and then see that the exposures are balanced. If the maturation of the drug is known, and for some drugs is known, or it can be guessed, because, for example, if a drug is going to be cleared, the maturation of glomerular filtration rate is known. Well, the tool uses the WHO weight for age growth charts to deduce what's the reasonable age range given a certain weight. This is because the dosing recommendations are given based only on weight, not on age. So just to be in keeping with that, the model, then the tool basically guesses what's the likely age for each specific weight. So this is basically an overview of the tool, but I'm gonna flicker through this very quickly because this part of the presentation was, meant to teach people how to use the tool, but it's embarrassingly simple for this kind of audience. But all it does really is you define the target dose, and as you can see in there, the tool can be used for fixed dose combinations. So that's another useful feature. One can display what happens when 3 compounds are dosed in the same tablet. So one can choose what doses are given in adults, the reference weight of the adult that we want to target. You can then define what is the content of the pediatric fix those combination and define the amount of each of the drugs. You can then define an acceptability range just to visually see if you're off or not from the target. And if you know about the maturation of the drug, you can enter in there the parameters of the maturation in terms of the age at which the maturation reaches 50%, and the gamma, which is the shape factor of the maturation. In the next step, you can the user is presented with the different weight bands, and initially the default weight bands for antiretroviral drugs are loaded in there. The user can decide how many tablets to give in each one, and they can keep playing with the results until the results are satisfactory. If one wants to design new weight bands, the same is available in 1 kilogram steps. And the outcome, which is that chart, is shows what the expected AUC is compared to adults based on allometry and maturation, if available. We have a quick example of when we apply this toolkit to amoxicillin, and you can see that on the left over there, there are the different weight bands, and the user then changes the number of tablets in each weight band, and the minimum and maximum you see within each weight band is shown with the reference being 1. The user can, of course, try different number of tablets, and the tool is going to display the results, and the number of tablets can be changed to then balance the exposure. It's all embarrassingly simple. And I shared this tool with the pediatric antiretroviral working group, but in fact, within WHO, people that work on different diseases fortunately talk to each other. So a few months after I shared this with the antiretroviral group, I got an email from the team that was developing the new guidelines for multi-drug resistant tuberculosis. And this is quite a tricky disease, meaning that some drugs have been discovered recently, but some of the other drugs are actually very old, and very little is known about how they work in children, and they are extremely toxic. So it's essential to try and give guidelines on how to dose these drugs without actually knowing how they behave in children with direct data. So you can look at this. This is the table of the dosing recommendations for multi-drug resistant tuberculosis, and of course I noticed because I knew. But if one looks in detail, and there is like a little subscript over there, I'm going to zoom it for you. What they have done is they, for certain agents, the dosages were informed by pharmacokinetic modeling results based on the principle of allometric scaling. And actually, they used the tool, and they asked me for a reference. I felt too ashamed of referencing my own tool, so I just gave them the reference for Nick Alford's, Anderson and Alford's paper on allometric scaling. So hopefully Nick is gonna forgive me for the boutade about this pharmacokinetics Tinder. But basically, yeah, this explains that due to the pharmacokinetic properties of some drugs, the proposed doses may exceed the milligram per kilogram ranges that are advised for adults. So this may seem like a very small thing, but in fact, it's incredibly relevant, and I'm almost ashamed that this got achieved with an Excel spreadsheet when the science to do this has actually been there for a very, very long time. Okay, at this point, I guess it's the time. I'm ready for the Rotten Tomatoes, meaning that I know I've been presenting an Excel spreadsheet to very distinguished modelers, and you guys are probably going to see the huge shortcomings of this and the huge limitations, but I hope you're gonna bear with me, meaning that I'm one of you guys. I also like my VPCs and my objective function drops and complex models. I have to say I started very nerdy as an engineer, and then working with clinicians, I understood that they don't really care about box-Cox transformations and other things like that, but I do like my models. Nice. So I know that there are lots of limitations in this tool, and I have outlined them here just to make sure that I'm dodging some of the Rotten Tomatoes that you guys are throwing my way. So, of course, this tool only scales for clearance, and it targets overall AUC, which is in general what you want to achieve. But for some drugs, you may want to care about Cmin and Cmax. And that one is a bit trickier to do, because for the same reasons why, for basically the same plot that I showed before, since the difference between the ratio between clearance and volume will change to allometric scaling, because they scale differently. So this means that terminal half-life of drugs is actually shorter in children. So what happens is that even if you target the same AUC, you're going to have a higher Cmax and a lower Cmin in general. And sometimes if the half-life is very short, you may have to split the dosing frequency to twice daily, for example. Another limitation is that maybe the population that you want to treat does not really reflect the standard WHO growth charts. If we're looking at TB or HIV children, those may be malnourished. So the imputation of age may not be accurate over there. Or sometimes the real descriptor for allometric scaling may not be body weight, or fat-free mass, making things a bit more complicated. Also, the tool just displays the typical values. So it basically displays what the AUC is with respect to the reference for a typical child. But we know that between subject variability is sometimes very significant in drugs, so that's not displayed in the tool. While one can argue that one can get rid of between subject variability, and it makes sense to target a typical person in the middle, this may be misleading. And the other issue, of course, is that this is a generic tool, so it's meant for generic drugs. But as I said, especially for the very young children, there are other factors that are very difficult to predict sometimes. And for those, the tool is just not going to cut it. And then I'd like to mention another limitation. Just before the webinar yesterday, I got this email mentioning an Excel spreadsheet, which is apparently very popular at the moment in the United States, and it's an Excel spreadsheet that has been used to predict how the COVID epidemic is going to advance. So Excel can be a very dangerous tool. Apparently, somebody just took the data from the deaths per day in the US, and they just pretty much put in Excel, called it a cubic model. But all they've done is they just put like a polynomial cubic spline or something very simple that predicts that all the deaths are going to become negative in a couple of days, and people are basing decisions on this. So I am well aware, point well taken. If things cannot be simplified too much, and you don't want to put tools in the hands of people that don't know how to use it. But the whole point of what I'm trying to achieve is that we use the Excel spreadsheet to put a foot in the door and raise the issue, and then make it more digestible and more approachable to the team of experts that needs to decide on dosing guidelines. But the plan is indeed to make things a bit more sophisticated. And in fact, the other part that I would like to briefly present, this is still a work in progress by one of my students, Chokosela Titiso, and he's working on a shiny implementation of the dosing tool, which is, so that is the website where it's hosted. It's actually on the shiny server of Professor Mark Laviel, so thanks, Mark. This also explains why you may get error messages in French if the server is too busy. And this is just a prototype. And what it does is, of course, it has the same features of the Excel version in a more intuitive interface. And this is still the generic part of the tool. But the additional part that we'd like to include, and the work is ongoing, is to add a drug-specific section of this tool. So this would provide a library of models for specific drugs, and this can just be taken from literature and coded in the Monolix language, which is very simple. And then by choosing a specific drug model, the user can then simulate the entire PK curve and decide whether they want to extract AUC or Cmin and Cmax, and see how this changes across different weight ranges, and so on and so forth. There is, of course, the chance of the opportunity of including between subject and occasional variability. And if the model has other covariates, we plan to include that as well. So I've just taken a couple of snapshots of this. So this is basically the part that is very similar to what the Excel spreadsheet already does. You can see that one can decide on the adult dose, define the number of tablets in each weight band, and then the tool is going to show what the exposure is going to be like, and one can include or not the maturation. The new part of the tool is more specifically about specific drugs, and one can select the drugs. We've only put 2 or 3 at the moment, but the idea is that any publication can just be coded in monoliths and added to the library, and one can simulate with that specific model. One can obtain the entire PK profile, change the dosing interval, etc., etc. Basically, it aims to be a very easy to use simulation platform to study drug dosing regimen in children. So I think I'm nearly run out of time. I hope I haven't gone too late. So the take-home message of the whole talk is I don't claim any credit for most of the science that is in here, because indeed, this has been known for a very long while, and a bunch of excellent scientists have studied this extensively, and they have, provided us with this very useful knowledge that helps us predict what dosing should be used quite accurately, at least in the older children. But unfortunately, that science very often remains in the ivory tower. It's just, in a nice paper, maybe you get a lot of citations, but at the end of the day, if the dosing recommendations are not changed, well, all that science is only gonna, get you some citations, but it's not really gonna get out there. So sometimes all it takes after years and years and years of science is one just has to sort of do the last couple of steps and try to make the science digestible and really take it where it needs to be. So in the way forward, we are gonna publish the tool. We have prepared the draft and we are submitting it. Yes, I am gonna submit the paper where I publish an Excel spreadsheet. And once it's out, we are gonna release the tool on the website for GAP-F, which is the Global Accelerator for Pediatric Formulations, and then eventually, hopefully, on the WHO websites, along, of course, with clear limitations. So this is, expected to raise the questions about, questioning the fact that constant milligram per kilogram should not be used. But of course, we're going to state that this is not a panacea that cures everything. And at the same time, we hope to keep working on the Shiny app so that we can provide a more extensive platform, which really substitutes what we would do in a modeling and simulation scenario to study a dosing regimen. And with this, I'd like to conclude, but acknowledging the people that helped me with this. So some colleagues at the Division of Clinical Pharmacology at the University of Cape Town, and of course, the team at the WHO Pediatric Antiretroviral Working Group. So thanks so much for listening. And Rebecca said that she's been monitoring the chat box if you guys have any questions.
Thank you, Paolo. Yes, we are taking questions. They can be entered into the questions pane on the GoToWebinar side panel. And we do have a few questions. Let me start with, the first one. If you have a compound with a high CV percent, is it also necessary to increase the dose in younger children?
I guess it depends on it depends on how tight the therapeutic range is, really. So if the drug is very, very variable, but at the end of the day, the therapeutic index is very forgiving, meaning that you have a very wide range where the drug works, well, then maybe all I've said doesn't matter as much, meaning that even though dosing the same milligram per kilograms, you achieve lower exposure, it may not change as much. But my argument there is that these dosing recommendations just need to be done once. They just need to be prepared once. So one might as well do it properly. And even if you have a drug with a large variability, sure, for the majority of people, it won't matter. But if your target dose is somewhat wrong to start with, well, you increase the chance that the extreme sort of outliers, either too high or too low, may not get the right exposure. So yes, in terms of how much this clinically matters, it depends on the therapeutic window of the drug.
Great. And I should.
Yes.
I was gonna mention we have a number of comments that say that to let you know that yes, They are laughing at the jokes.
Okay, I'm glad. I'm glad. I hope Nick is one of them. Otherwise, I may write him an apology. No.
Actually, yes.
Okay.
So the next question is, the author says, I agree completely that fundamental PK/PD is no way undermined by modeling. I would like you to comment on where you draw the line for saying pharmacometrics versus not pharmacometrics. Can the spreadsheet you showed not be considered pharmacometrics, as in quantitative clinical pharmacology?
I guess that's a philosophical question. So I would say it's definitely a non-conventional tool, but I guess it has a bit more science in it than a spreadsheet assuming that everything doubles linearly or something like that. So I don't know. I guess we could run a survey in the audience whether they think that this is pharmacometrics or not. I mean, the principles behind it are definitely pharmacometrics, and I think my aim was indeed to use a sort of less scary tool to bring pharmacometrics principles out there to those that maybe get a bit scared when they see all the differential equations and such. And along those lines, I guess the Shiny app will probably be even better because that's even a more controlled environment and more flexible. And I think that as long as the principles are there, ultimately this is pharmacometrics. But claiming that I developed a sophisticated pharmacometrics tool with a spreadsheet, yeah, I wouldn't go that far.
And they ask, when will the Shiny app be available?
So the Shiny app is already there. Please don't click all at the same time because it may crash. And it's still pretty much under work, and we have to improve the usability. So after the webinar, the slides are going to be shared, and in there is the link. The link, there it is. So it's on the Shiny Web Topics website, which is hosted by Mark Lavielle. He's got a whole bunch of other Shiny apps. So it's over there. So this is still a prototype. And in fact, what I'm going to do is, well, if people have comments or any feedback on how to improve it, they should, please email me. I'll share my email address as well, because of course, any feedback is welcome there. Be kind because it's still work in progress. I think the main features are there, but yeah, the usability can be improved. But if you have any suggestions, please let us know.
And do you see this being expanded to other populations and to other drugs?
So the principles are general, as I said, meaning that especially allometry, that one ranges completely. For any child older than 2 years, that's exquisitely, well, not only, but it's the main driver of differences. So it's valid for most drugs. Beyond that, it gets a bit more tricky, but even those principles can be generalized. What is different, I guess, between anti-infectives is that in this case, we can assume that the exposure response curve is very similar, because ultimately we are trying to kill the same pathogen. So it makes sense that if we achieve the same concentration, it's going to work in a similar way. So for other disease areas, things may be more complicated, and one may have to study the PD as well. So if the PD relationships, the exposure response is different in children, well, then achieving the same exposure as adults is not going to cut it. In terms of whether this can be used for other populations, well, yes. In fact, it can be used for adults as well. Even the adults guidelines are wrong. For tuberculosis, there are also dosing guidelines that target the same milligram per kilograms, and they tend to underexpose smaller adults, which in this case tend to be malnourished and very sick. So they have a low weight, not because their constitution is small, but actually because they're sick. So they are the ones that arguably need the drugs the most, and they end up being underexposed. Another complicating factor is that sometimes the real driver for the differences in clearance is not total body weight, but lean body mass or ideal body mass. So when somebody is, for example, overweight, maybe their weight is 150 kilograms, but that weight doesn't predict the size of the liver or the size of the kidneys. So one may end up actually overestimating the clearance for those patients. So in that case, the tool would have to be tweaked to include the scaling with fat-free mass, but yes, it can be adapted. At the end of the day, it's a sort of simulation platform, and this is geared towards children. But as long as one is interested in looking at weight, this can be tweaked easily.
And for the anti-infectives that you discussed, the question asks, can you really assume that the PD is the same in young children? The role of the immune system is vital in clearing infections and may be immature in very young children.
That is very true. That is very true. So it can work differently. So for tuberculosis, it's actually the other way around, meaning that, well, some children do get TB meningitis or miliary TB or very serious TB. But at least here in South Africa, most children receive the BCG vaccine, which is becoming very popular now because they think it may protect against COVID as well. And this is aimed at preventing this extrapulmonary TB. But for pulmonary TB, actually, disease in children is actually milder. They tend to do better than adults. For malaria, it's the other way around, because generally children do not have the same immunity that older individuals may have acquired against the parasite. So in those children, one would argue that, yeah, they need the drugs more than others. And of course, different diseases may work differently. So yes, the immune system is going to be different. I guess, so that doesn't necessarily change, how well the drugs kill the bug. It changes how the immune system kills the bug. So yes, that should go in the picture. So yeah, point taken. One can't assume 100% the same. But I guess that decisional tree at the beginning was aiming at, really separating some therapeutic areas where, the entire pharmacodynamic biomarkers are completely different, and one just can't use the same techniques. But yes, point taken. It's not always 100% the same.
And can you tell us where your research with this tool will be going next? Will it be going to different drugs or changing direction?
So we are working in collaboration with the WHO group that is working on antiretrovirals. So the idea is to first focus on a tool that can be used internally for decision making, but at the same time, this is going to be available for anybody that wants to use it as well. And as I said, it can be used for other drugs. So the first focus of this is really HIV and probably tuberculosis. Because it's a useful tool to just have an overview of what the different models predict the exposure are going to be with the different scenarios, and it allows to evaluate those scenarios before they get sort of rubber stamped and be put and are put into the official policy from WHO.
Great. Okay, I think we have answered all the questions. I would like to thank our speaker today. Paolo, it's been a really interesting and informative webinar, and I was very pleased to see that a spreadsheet can work if done properly, as well as a standard PK/PD model. So with that, I'd like to thank you for presenting today, and I'd like to thank our audience, and I hope to see everybody again at a future webinar. Thanks, Paolo.
Thanks so much. Cheers.
Have a great day, everyone, and I hope everyone stays safe, and see you again soon.